Let's review double integral for a sec. When we did double integral, it looked like this. So we have some kind of right. This is our region. How do I wanna? Yeah, let's say this is our region. That looks like this. This is our D. Okay, somebody just came in. Okay. Skylar, you're late and you messed up our video.
Sorry.
I'm gonna restart. Okay. Take two. Okay. Today's topic is triple integral, but let's review our double integral for a sec, right? If we have our region D, and then we can set it up this way. So double integral of D of f of some two variable function and dA, right? We can calculate in x direction first. I mean the y direction first. So this is, let's say, y1, and this is y2. This is, say, G, and this is H. Good. So this is f of x, y, and then you want to do dy first, and y will vary from G, which is y1, to H, function of x. You know what I'm saying? This curve to that curve, and then A to B. We set it up like that. Or we can go sideways and from this curve to that curve, so x1 to x2, and then you do dx and then dy, right? That's what we've been doing. Now we have to do triple integral. And what does that look like? Okay, so when we do triple integral now, we already have three-dimensional axis, right? Triple integral looks like this. Right, and our function is three variable x, y, and z already, and then this thing is dv now instead of dA. And over some volume, I think our book calls it E for some weird reason. Let me just double check that. Yep, E. I don't know why it's E, but it's E. Okay, so let's sketch our region, and this gets really complicated. So we have, let's say we have what, z-axis right there. And let's say this is our y-axis this way. And then x-axis like this. Okay. And then our region is some 3D shape. Something that, let's say, hovers about like that. Right? Okay, and it's going to cast some kind of shadow onto XY plane. You know what I'm saying? So this is E. This blob is E. That's what we're integrating over, volume integral, if you will. And it's going to cast some kind of shadow here, right? And we'll call that D. Good. So far with me? So when we rewrite this integral, first we have to cut it somewhere. Let's say this is like side boundary. So we can have an upper half of the surface and bottom half of the surface. You know what I'm saying? So this bottom one, I'm going to call it z1 is equal to some function. This is a two variable function, x and y. And this top one, we can call this z2 is equal to h of x and y. You know what I'm saying? So for now, it has to go from z1 to z2. So this has to go from g of x and y, two variable functions. Surface goes here, and then h Do you understand kind of what's going on, or is it like what? And then we can put dz. You with me? Just like in this case, we went from this bottom curve to top curve. That's about to happen, but we have 3 of them now, so it's a bottom surface to top surface. And do I want to attempt to draw that arrow here like this way? No, let's not. That looks like awful. You know what I'm saying? Now, and then after taking care of that, now it's a case of a double integral now, isn't it? So on this, suppose we want to do y next, and then this is some kind of y function, right? So I'm going to call this like y1 of x, and this is y2 of x. You get it? So then we put here y1 a function of x, and then y2 function of x, and then dy. Good. And lastly, the constant term, and then let's say this thingy here is a, and this way is b. Good. So the x varies from a to b. How about that? Do you want me to redraw this thingy down here next, or did you get it? How many of you want me to redraw this region and then it's just like this case? You know what I'm saying? Okay, so that's how you want to evaluate triple integral. Why don't we take an example? Because like half of you are saying what is going on, right? Okay, we have this example. So we have, this is our function, x squared plus z squared, and the square root, that is an awful function, dv, and that dv, dx, dz, dy, dx. That thing itself is this thing. So its intersection is bounded by the region, bounded by this paraboloid, sideways paraboloid, feel it? And then y is equal to 4, so we cut it off like that. Good. And this will turn out to be an awful integral, okay? Let's just set it up and not evaluate it, and I'm going to show you much, much better way, okay? So I'm going to set it up here. So triple integral e of our square root of, what was it? X squared plus z squared dv will turn out to be, okay, let's first figure out bottom surface to top surface, right? So that bottom surface, do you see that from here? This c is plus or minus, so negative square root of y minus x squared like this. This is z1. And then this one is z2, which is square root of y minus x squared. Do you see that? This one is that one right there, and this one is this one right here. So our lower limit is negative square root of y minus x squared, and upper limit is square root of positive y minus x squared. You with me? Okay, and we have our function, which is x squared plus c squared, and then dz is done. Now the other one, now the shadow of that thing, or intersection, cross section of that thing is drawn right here. Okay, so we'll move this way, and in other words, this way, right? So we have this is y1 and this is y2. Do you see that the cross section right there? Let me try to throw this in a way it makes sense. That cross section is our region D. Do you see it inside that picture? Right, that our D is always on XY plane or some kind of plane. Okay, so this thingy, your limits of integration has to go from y1, which is x squared, to y2, which is 4. Good? Right? And then finally, this is -2 and +2, right? Pretty awful, isn't it? How are you gonna evaluate this thing? I sure don't know how. So we have to get creative, especially when it comes to triple integral. And I remember when I was taking this for the first time in college, one of the questions was you have to rewrite this integral. I mean, actually, that professor didn't even give me this kind of thing. They gave me this, and then we have to imagine this whole thing and then rewrite it. And the way you rewrite is you rotate this thing around and stand it up. You still have to imagine this thing and then rotate it in your head. And then you have this picture. I kind of use the computer to rotate it, so it's like sideways drawing. But so we have z, x here, and y there. If you put your head, tilt your head 90 degrees, then you can see it's the exact same picture as before. You know what I'm saying? And then we'll try to change the order. Okay, so let's attempt this. So first thing is this bottom surface to top surface. So this one right here, I'm gonna still put it in red. This one is, oh, not z anymore, this is y now, right? So this is y1, which is x squared plus z squared a. And this top one here is y2, which is equal to 4. Do you see that? Okay, so our triple integral here, our e, and then we have square root of x squared plus z squared, was it? And dv. Now we can rewrite this as, I'm gonna leave lots of space because for some reason these spaces are just getting cramped up. So from this y1, so we have x squared plus z squared to 4. And we have the rest of the functions, square root of x squared plus z squared. And then we have dy, and that y is ugly. And then rest of them, I'm gonna put still dA. How about that? Turns out I didn't need all that space. Climb it back. You with me? And then dA. Now this is going to cast a shadow down here. Actually, I'm gonna draw it. I'll just draw it here as. See, the shadow of this thingy down here will be like that. You know what I'm saying? And I'm gonna draw that as a different region. And so that's what I'm gonna draw here as a D. And I'm gonna draw D for you down here. About the same size, right, like that, right underneath it. You know what I'm saying? And this is D. And this is x-axis versus z-axis now. Are we good? Say yes. And then this should be 2 and then negative 2a. Like that. Who's lost? This is not an easy stuff. This is confusing stuff if you are not on top of everything. So if you're lost, now is a good time to let me know. I'm going to put it right underneath so you can see that's that shadow. Okay. Okay then. Shall we start evaluating that much? Okay, and the reason this is an easy integral is, look at that y. There's no y here, so this whole thing is a constant now, isn't it? So we don't have to really set up the rest of it. We can just go like this. So what we have is, this is equal to the double integral, which will worry, why is my integral sign so ugly today? Slightly better, d, and this is just y. I just put y here, and square root of x squared plus c squared, and I regret that action. I'm gonna go back. It's constant first, x squared plus c squared, and color coordinate, and we just have y like that, right? And y will vary from x squared plus c squared to 4, and we have the rest of the dA. Are you with me? Because the y did not appear in the first integral, so that one was easy. Good? Okay, now I'm going to substitute. So what we have is still the double integral. So we have 4 minus, right? We have 4 times this thingy, x squared plus c squared, and then minus x squared plus c squared, and is that square root and same thing, so it's a 3/2 power. Are you with me? Are you with me? Too much algebra. Okay, now you're thinking, oh, how are you going to integrate this now? Because our region looks really ugly too. Brilliant suggestion. I will take brilliant suggestion at this point.
Polar.
Of course, why wouldn't we go polar, right? This is circular. Wait, this is x and z, not x and y. Is it okay? Can we still go polar? Why the hell not? Because the x, z, x, y, these are all going to disappear. This value of the integral is constant anyway, right? So these little variables don't care what they are named. I mean, we name them anyway. So we go polar. So let's go polar. If we go polar, then now this thingy, first thingy is just, that's r, isn't it? So we have 4r, correct? And that's r squared, correct? So we have minus r cubed. Ain't that nice? And then remember dA was another r, then dr, and d theta. Remember that? Okay, then r varies from, oh, this is really nice, 0 to 2, and theta varies from 0 to 2 pi. Huh. Now it's all downhill from here. Can we distribute and integrate at the same time, or is that too much in algebra calculus combo? Too much integrity? No? We can do this? Can you handle this? So this is r squared, right? So it becomes r cubed, therefore 4/3, minus, this is r to the 4th power, so r to the 5th, therefore 1/5, right? And then from 0 to 2, and then we have the data left. Almost there. So far so good? Oh, our most challenging part, multiplication addition. And then there's no theta, so this just becomes theta, and then we can pick up 2 pi, right? Let's do that much in our head. Over 15. Dang, huh? How do you like triple integrals?
Mr. Kim, this is just
Yes.
a small thing, but you're missing a square over z's in the 4 square root of x squared plus z squared minus the quantity of x squared, and then you have regular z instead of z squared to the 3/2 power.
Wait. Oh, that's squared. Oh, yeah. Of course, that's there. That's how am I gonna squeeze this in? There. Erase. This one notice. Oh, okay. So this is plus z squared and 3/2 power, right? Like that. Okay, good. Thank you. Anything else? Any other question? It takes a lot of imagination to draw this thing because it's not that easy, but let me put it in UCalc and then show you what this thing looks like, okay? So we have the cylinder. Do you see the cylinder? At least. So we have y squared plus z squared is equal to 1. So we have the cylinder that's running in x direction, right? This is x-axis. And then we are going to cut this by the plane y is equal to x. Like that, at a slant. So far so good? And then we are going to put another plane, x is equal to 1, but I don't want to put that on because then you cannot see this thingy. Right, x is equal to 1 will go through this. Actually, I think I can put it. So we want the volume of that wedge right there. You get it? This wedge. You know what I'm saying? So that's what's going on. And I'm gonna throw this sketch, but you should have this idea. Okay? I'm gonna close the new calc now. Okay. Now let's try to sketch that. This is not an easy thing, but at least this is in the first octave. Okay, so I'm gonna draw this axis first. When you are drawing these axes, there are a couple of styles. You can do it this way or you can do it that way, right? Depending on your purpose. But for this purpose, I think this style works better. Okay, now, then remember cylinder runs through the x-axis, right? So what I'm gonna do is, let's say this is 1. Create something like that. So that's that cross section. Actually, I'm gonna make these things blue. Okay, and then create this cross section. These are the easy parts. And then what we have is, now here comes the difficult part. Let's see if I can trace this thing. This is a cylinder that runs through. You know what I'm saying? So on the other side, it would have been this. You know what I'm saying? However, we're cutting it right there. along this thingy, which is y is equal to x. We're cutting it right there. You know what I'm saying? Maybe this should be in a dotted line. That's ugly dotted line. Why am I so? Don't answer that question. So we're cutting it right there like that. So this thingy now has to run like that. That's the wedge, the volume that we're trying to find. You know what I'm saying? Okay, so like, yikes, how are we going to do this now? Right, so let me label this thing. So this thingy right here is x is equal to 1. And this thingy right there is x squared plus, y squared plus z squared is equal to 1. Okay, and this thingy right there is y is equal to x. Okay. Now, so this is just the volume, so let's just write it as triple integral. V is equal to triple integral of dv. But which one do we want to do first is the case, right? Remember, this thing runs from surface to surface. So do you want to go from here? If you want to do z first, you have to go from bottom here to that surface. You know what I'm saying? And the region that on your xy plane is that triangular shape. Or do you want to go from this bottom part to there, right? Or do you want to go from that back towards the x-axis? And it looks like from the geometry, doing x first looks more convenient now, doesn't it? And the rest of them, we can go polar. You know what I'm saying? So we should definitely go x first, and then we'll just leave this as dA. How about that? Now, so this is our region, we'll call it D, and D is that thingy right there, that quarter of a circle. You with me? That's ugly dx. Oh, that's even uglier. What am I doing? Okay, didn't get better. And now, from what to what then? Do you see that from y is equal to, x is equal to y to x is equal to 1? Do you see that? Do you see this needs to be then x is equal to y to x is equal to 1? This is x. Why is my handwriting so bad today? Do you see that? Okay, let's evaluate that. So this just is double integral in our D. You just pick up x and then this becomes 1 minus y then, doesn't it? You with me? And after that, that D is this quarter of a circle region between your y and z, but nothing's stopping us from going polar on this anyway. You know what I'm saying? So we'll go from 1 and then y, of course. We'll use, so y is still r sine theta. Do it that way. And then z could be x-axis equivalent. Or we can put cosine here and z is a sine. Doesn't matter. Is this good for you? Okay, and then we'll have to have r, dr, and d theta. So far, so good. And then our r should vary from 0 to 1. Good, this is 1 right there, isn't it? I know, that's why we decide to do x first and rest of them go polar, so these are not functions, you know what I'm saying? And then your theta will vary from 0 to pi over 2. That'll work out nicely, eh? Okay, then only one thing left, which is showing our integrity, 0 to pi over 2, and this thing becomes r. Oh, can we distribute and integrate at the same time? So this is already r here, so we have r squared over 2. And then minus, that's also r squared over 2. Hey? Wait, that's r squared, so this is r cubed over 3. And then times sine theta from 0 to 1 theta. You with me? Okay, simplify that, so 0 to pi over 2. And then we have, this is 1/2 minus 1/3 sine theta. Good. Now we'll integrate that. So we have 1/2 theta minus becomes plus, and then 1/3 cosine theta from 0 to pi over 2. Good. So substitute pi over 2, so we get pi over 4, and this becomes 0. Now minus 0, and then that thingy becomes 1/3. How about that? Good. Questions? So only thing that was difficult was this thingy, right? Imagining this shape. That's why I had you sketch the quadratic surfaces, because this is a unique talent. Most people cannot do it. But all of you could now, right? Say yes. Okay.